These are your chi-square testing notes 2, goodness of fit, day 2. The purpose of a chi-square goodness of fit test is to see if the proportions for our observed data are the same or different than some pre-established expected proportions. Observed sample data or your total counts will typically appear in one row or one column in your table. Now, the whole point of a chi-square test is the idea that we're working with two or more proportions. You may remember in our last unit we did something called a two-proportion z-test, or we even did a one-proportion z-test. Chi-square tests deal with two or more proportions. So instead of doing something called like a 5-proportion z-test or a 12-proportion z-test, anything from 2 and above can all be kind of characterized in terms of a chi-square test. Let's take a look at a few examples. In our first example here, it says that the proportions of green, red, yellow, and orange and purple Skittles in a bag different. And we have these observed counts in a table that consists of basically one row of data. Your hypotheses here can be written a few ways. If you're thinking about how we did work last unit with proportions, what you could say is something like this. The proportion of green Skittles equals the proportion of red Skittles equals the proportion of yellow Skittles equals the proportion of orange Skittles equals the proportion of purple Skittles. Or you could use wording from the question. If the question is being asked, are the proportions different? The null hypothesis would be, no, they're not different, they're the same. So you could also say the proportions of green, red, yellow, orange, and purple Skittles in a bag are the same. For our alternative hypothesis, if we're answering yes to this question, are the proportions in the bag different? What we're going to say is this. Maybe some of the proportions are the same. Maybe green and red both come up 20%, but maybe some of the other ones don't. So what we're going to say is this. At least one of these proportions is different. And it is possible for exactly one of those proportions to be different if maybe all these proportions are like around 18%, so you have like 4 colors that are each 18%, and then one ends up being, closer to 30%. Okay, one of those is significantly different than the other 4. You could do something similar for the second question. Does the grade distribution of athletes on a swim team differ from that of the student body? For your null hypothesis, you could say basically no, they're the same. If you want to use numbers from the problem, you could do that. For example, P9 for 9th grade being freshmen is 0.23. The probability of a 10th grader, the proportion of 10th graders is 0.25 on the swim team. The proportion of juniors on the swim team does match the student body value of 0.26. And the probability of being a senior on the swim team is 0.26, which matches the student body percentage. You could also use words. The grade distribution doesn't differ. For your alternative hypothesis, again, maybe a few of these percentages are pretty close, but maybe one is off. As long as at least one of these is different, then we would have to reject our null hypothesis, and we would say that at least one of these proportions is different. This will always be your alternative hypothesis for our chi-square goodness of fit test. At least one of these proportions is different. We're going to take a look at problem 13.2 on page 736 in your book. This was a problem that we had for homework from the other night, where all you had to do was carry out the procedure, calculate degrees of freedom, and the p-value. I want to take a look, if we were to set up all the steps for this type of problem, what would some of these different steps look like? So I'd like you to get out your homework problem from the other night. I'd like you to pause the video while opening your book to page 736. Once you have your homework and your book out to the correct page, we'll restart the video and we'll take a look at some of these parts for this particular chi-square test. First, let's start with our hypotheses. There is a statement that asks us to determine if the marital status distribution of U.S. males 25 to 29 years old differs from that of the U.S. adult population. So your null hypothesis, one way of saying this is you could do something like P sub never married equals 0.281, P sub married equals 0.563, P sub widowed equals that, P sub divorced equals this. You could say something like that. You could also say the marital status distribution of U.S. males 25 to 29 years old does not differ from that of the U.S. adult population. I think you're safe using either type of method here. For your alternative hypothesis, at least one of these proportions is different. For a goodness of fit test, you can always use this alternative hypothesis. When you're doing a chi-square test, when we start working with our conditions, we obviously want to check the random sample condition, but then you also want to do what's called an expected counts table. To calculate our expected counts, what we're going to do is we're going to take n, our sample size, and we're going to multiply it by our expected proportions. The sample size in this problem is 500 US males. So what we're going to do is we're going to multiply 500 times each of these values that were listed as sort of our observed values. These are the observed percentage of people in the population that have these categories. So what we're going to do is we're going to multiply each of these observed proportions by 500. And we'll write those numbers inside the chart here. Again, how do we generate these numbers? We're going to take each of these observed proportions, each of these percentages, and we're going to multiply each of these numbers by 500. That's where these numbers come from. For condition 2a, what we need to check is we need to check to make sure that each of these values here is at least equal to 1, and that's true. And then for the second part of the condition, we want to check that no more than 20% of these values are less than 5. In this case, none of them are less than 5, and that's a good thing. So we want the expected counts to be big. They have to all be at least 1, and we really want to avoid any of them that are less than 5 if possible. But we're allowed to have 20% if necessary. Here we don't have any, and that's good. In the future, if you have none of these expected counts less than 5, what you can say is that all expected counts are at least 5, and that actually addresses both of these conditions. The next thing we're going to do is carry out our procedure. We're going to calculate what chi-square is equal to. For chi-square, we take each observed value. Now, these are the numbers that were originally in your table, like the 260, 220, 0, and 20. These are observed. These are actual values. And we're going to take each of these values minus the expected numbers that we calculated in our little table here. So based on percentages, we would have expected 140.5 of these 25 to 29-year-old men to be never married. And we're going to continue taking numbers that were originally in the first table, and we're going to subtract them from numbers that we calculated in our expected table. We square these differences, and we divide by the expected value. And we'll do this for the other two values in your table as well. From your homework from last night, you should have actually calculated this value on your calculator. This is equal to about 161.77. Your degrees of freedom equal the number of categories. Here we have 3 categories, so n minus 1 would equal 4 minus 1, or 3. And the p-value is found using the chi-square CDF function. You'll find that under the distributions menu on your calculator. Typing in that number, comma 99, comma degrees of freedom. On newer calculators, I think it says lower bound, upper bound, and then degrees of freedom. So if you actually do chi-square CDF, this 161.77, comma 99, comma 3, you'll get a p-value. In this case, it's very small. It's in the neighborhood of 7.6 times 10 to the negative 35th power. And if you said it's approximately 0, that's doable. So what we're going to conclude with today is a problem from a past AP exam. This is from the 2003 exam. Contestants on a game show spin a wheel like the one shown in the figure shown. Each of the 4 outcomes on this wheel is equally likely, and outcomes are independent from one spin to the next. The contestant spins the wheel. If the result is a skunk, no money is won, and the contestant's turn is finished. If the result is a number, the corresponding amount in dollars is won. The contestant can then stop with those winnings or can choose to spin again, and his or her turn continues. If the contestant spins again and the result is a skunk, all of the money earned on that turn is lost and the turn ends. The contestant may continue to add to his or her winnings until he or she chooses to stop, or until a spin results in a skunk. Now what we're actually going to do is we're going to bypass parts A and B and move right into part C. Part C says a contestant who lost at this game alleges that the wheel is not fair. In order to check on the fairness of the wheel, the data in the table below were collected for 100 spins of the wheel. Based on these data, can you conclude that the 4 outcomes on this wheel are not equally likely? Give appropriate statistical evidence to support your answer. what we're going to do is we're going to do a lot of pause the video, see what you come up with, and see if it compares. So first step is, let's see if you can develop the null and alternative hypotheses. Pause the video, and we'll see what you come up with. So here's one option for your null hypothesis. You could say P sub skunk equals P sub $100 equals P sub $200 equals P sub $500, where P sub K is the proportion of times the wheel lands on K. So I'd like to explain to the reader what this proportion actually represents. The alternative, at least one of these proportions, is different. Now you can use wording from the problem if it asks, can you conclude the 4 outcomes on the wheel are not equally likely? For the null hypothesis, you could say the 4 outcomes on this wheel are equally likely, and the alternative still would be at least one of these proportions is different. In the problem itself, you'll notice that it doesn't mention anything about a random sample. However, outcomes are independent from one spin to the next. So what you spin on one spin has no impact on the next spin. That's one of our conditions. It doesn't have to be random sample if independent observations have been taken. So we'll write that down. For our second condition, what we need to do is we need to come up with our expected values chart. Now we have our observed values. That's what's in this chart right here. These are observed values. We need to generate our expected values. So to come up with our expected values, I'm going to use our table here. I'm going to label expected values, and I'm just going to add a little addendum to our current table that's right here. Altogether, we have spun this wheel 100 times. That's what you get if you add these numbers together in this row. So to calculate what the expected values are, is we're going to multiply 100 times each of these probabilities. Now, if each of these proportions is equally likely, this would be 25% for each one. It's like 100% divided by 4. So if you do 25% times 100, each of the expected values should be 25. The expected sum should equal 100, just like it did over here. And if all these events are equally likely, they should occur an equal number of times. What you'll notice is that all of these expected values are greater than 1. We don't even have to worry about the 20%. We're allowed 20% to be less than 5. None of them are. So if you just want to use kind of a blanket statement, all expected counts are at least 5, that's fine here. Now we get into calculating our chi-square statistic. Chi-square is equal to the sum of each observed value minus the expected value squared divided by the expected value. So we're actually going to crunch this out. What I'd like you to do is see if you can crunch out what this would look like. Pause the video, we'll see if your expression looks good, and we'll see if you actually can calculate the correct chi-square value. While you're at it, see if you can find the degrees of freedom in the p-value as well. So here we have our chi-square statistic. It's equal to 4.24 degrees of freedom. There are 4 categories, so it's not going to be 99. It's not 100 minus 1. It's 4 minus 1, which equals 3. Your p-value is 0.2367 from your calculator. And now you know how the conclusion works. See if you can write the conclusion based on this p-value. We'll pause the video one last time, and we'll see what you get in just a moment. So we'll say since the p-value is greater than alpha equals 0.05, we fail to reject the null hypothesis. We're not rejecting it because the p-value is big. There is not significant evidence that the 4 outcomes on this wheel are not equally likely. Now you're probably looking at this going, well, these numbers aren't equal to 25. True, but they're in the neighborhood. 26 is obviously pretty close. There's not enough evidence to go, wow, this is totally outlandish. I think it would be very possible to get this distribution here or something even more extreme. Now, if some of these values were a little bit higher, maybe if we had skunk that was around 40, maybe this p-value would get a bit smaller. But based on our data here, based on the math, there's not enough evidence to say that this wheel is really truly rigged.